Welcome back to this session in the afternoon. This session starts with a keynote speech. So I introduce the keynote speaker. It's my pleasure to introduce Professor Hidehiko Masuhara of the Institute of Science Tokyo, formerly known as Tokyo Tech. He has made an outstanding contribution to programming language design and programming environment. His work includes aspect-oriented languages, context-oriented languages, and meta-compilers. So please start.
Thank you. Thank you for a nice introduction, Uga-san. And it's very honor to give a talk here. And I changed the title of my talk as a joy of tracing just-in-time compilation more than just a JIT compiler generator. Because when I prepared my talk, I wasn't sure what I'm going to talk, but in the end, I realized that this is something about making the meta-tracing just-in-time compilation to do more than compilation. And I think I'm given 40 minutes for this, including questions and answers. So I guess it's better to accept the questions in the middle of the talk. So if you have any questions, then please interrupt me. And sorry for online guys. And this talk is mainly about the work jointly done with Yusuke Izawa, Carl Friedrich Boltz, and Yusei Yoshimura and Yudai Tanabe. And let me start with very short introduction about the meta-JIT compilers and also partial evaluation, also known as the Futamura projection. Introduction to partial evaluation in 1 minute. So partial evaluation is a program transformation technique by providing a partial input to the program. And usually, for example, can I show a pointer? Okay. So let's assume this program that computes the typical program that computes the nth power of x. And we specify the partial evaluator. We are going to give only input n. So then usually partial evaluator analyzes the program which depends on the n and which doesn't depend on or depends on x. And this red box part is depending on the value of x, which we call dynamic code, and then given a static input, which means the n, for example 5, then we execute the program for the only static part of the code, and emits the dynamic part of the code, and then we will get this kind of result. So the x times x times x times x times x times 1. This is partial evaluation. You understand everything. All clear. Okay. Then partial evaluation gets more interesting if we partially evaluate programs with respect to an interpreter. In my slide, I write eval for shortness, and because if we partially evaluate an interpreter with respect to the interpreted program, then we will get a compiled code. So this means the partial evaluator can compile programs. And let's also see by an example. Here's a code, which is a tiny interpreter that interprets a bytecode program, which gets the code as a bytecode, sequence of bytecode, and the argument to the bytecode. And then this is just typically interprets the fetch instruction, interpret if it's multiplication, then manipulates stacks, and then advances manipulates the stack pointers, program counter, and so on. And if we specify this is, we only want to partially evaluate the code input, and then those red part is dynamic part, then if we provide the source code, which is a bytecode sequence, then we will get this kind of compiled code, which only consists of the manipulation of stacks, and there are no code that manipulates this code parameter. So in that sense, this partial evaluator compiles from this source code into that compiled code. Okay, so introduction is over. Now, next introduction is about the meta-JIT compiler frameworks. Famous things are known as the RPython or PyPy and Graal Truffle. And those frameworks can generate a virtual machine from interpreter description. So, for example, if we write an interpreter of JavaScript and put that interpreter description into the RPython framework, then we will get a JavaScript virtual machine for JavaScript virtual machine. So this is very nice because if we can only write different interpreters of different languages, we will get the virtual machines of different languages. So so RPython and Graal Truffle are successful of generating the virtual machines for Python, JavaScript, Ruby, Smalltalk, or even for LLVM. And if we look inside of the virtual machine, then we can consider this virtual machine consisting of the two parts. One is interpreter part, which is just a compiled code of the eval, and also the just-in-time compiler for L. And this interpreter basically executes the program and find hotspot, and then run the just-in-time compiler to get the compiled code. So then if we look this figure, then we see that this framework gets interpreter and do compilation. So this looks like doing some kind of Futamura projection. But I was actually not sure. And actually, this is a quote from the paper written by Carl Friedrich, both in original PyPy's paper. Then it says, conceptually, there are some similarities in partial evaluation to PyPy work. So he wasn't sure. And actually, I was asked by Carl Friedrich around this time whether what he was doing is partial evaluation or Futamura projection or not. And at that time, I couldn't answer. Maybe similar, but I am not sure. But now I think I can answer this. But in order to answer to that, I need to explain in more detail about the meta-tracing JIT compilation mechanisms, in specifically what RPython does. So from now on, I'm only going to talk about the meta-tracing JIT compilation, so based on RPython framework. And then again, RPython takes interpreter or any kind of program written in RPython. In this case, we use same bytecode interpreter. And then RPython first compiles this interpreter into C program. So this is an intermediate code that RPython compiles, and I'm only showing this handler part, this part which handles the multiplication instructions. And you don't need to understand this code, but this is basically just a compiled code. And then we specify which part of the input is static and dynamic. Again, this red part is dynamic part. And then what next thing to do is to run the program. And in this case, we provide both static and dynamic input. So the static part is bytecode instruction set, and the instruction stream, and the dynamic part is some argument to this interpreter. Then the partial RPython or the framework actually executes this program and then creates a trace of execution. And trace is a series of instructions that was actually executed on particular run. And then in this case, for example, in the middle of this code, there's a multiplication instruction. So inside of the trace, it also contains the trace of the executed instructions, and also the values used for execution. So those green and red values are actually we observed during the execution. And then what the next thing to do is to remove static code, which means the instructions depends on the only green values, and then also embed, then we will only see those 4 instructions, and then embed the static values into the instructions, and then compiles those intermediate code into the native code. That is basic idea of the RPython's meta-tracing JIT compilation. Is this clear to you? Okay, then by explaining this, I can now clearly say that this is the first Futamura projection. And the relationship or difference from the original Futamura projection or partial evaluation to this tracing JIT can be explained in this way. So the partial evaluation partially evaluates static code and emits dynamic code. So it only executes static code. Whereas the tracing JIT actually fully executes the program while and also fully emits the code. So both static and dynamic parts are executed, and both static part and dynamic part are produced as an output. Afterwards, from the emitted code, which means trace, we remove the static part of code, we will get the partially evaluated code. So it looks slightly differently, but effectively both are doing the same. So I hope you are agreeing. You agree with me. Okay. Then introduction is over, and then what are interesting part? So the real part begins from now on. Okay. So then what I want to show you is what I have shown you is a meta-tracing JIT compiler can compile programs. So it generates the JIT compilers, but it can do more than that. So as I have shown, if we give the language semantics as an interpreter, then the meta-JIT framework can generate the JIT compilers. But if we specify something different, like code traversal, so not just the language semantics, but something what compilers do, then we will get some interesting behavior of the virtual machines, like a method compilation, threaded code generation, or even more, we can do some kind of optimizations like inline caching and the multi-tier compilations. I'm going to explain one by one. So method compilation. By the way, I haven't explained explicitly, but the meta-tracing JIT compilers is a tracing compiler, which means if there is a conditional branch, then it compiles only one branch actually executed. And the method compilation usually compiles the whole method. That means if there is a conditional branch, then it compiles both then and else branches. So then by tweaking the meta interpreter definition, we can get the method compilation by using the RPython framework. Let's see how we can do that by actually changing the semantics of branch. So here is a semantics of branch instruction, condition jump if 0, and which is basically checks this top of stack is 0, and if it is 0, then then update the program counter to the jump target, which is very simple and very clear to you, I hope. And if we change this semantics into this way, so that the first emit the if instruction, and then recursively calls the interpreter from the next instruction. That means we just use some trick to generate the direct code directly. So we emit if instruction, and then the next thing is generate from the else part, and then generate a label, and then continue execution or evaluation or compilation of the jump target. So this is an interpreter definition, but it also looks like a compiler definition of if then else statement. Compile then else part, or generate if instruction, compile else part, generate label, compile then part. And if we provide this interpreter definition into the RPython framework, then we will get the method compilation so we can get the both then and else branches. And of course, this is not as easy as explained on this slide, so we need to do more on the dark side, but I don't have enough time to explain that. If you are interested in, then I can explain later. Anyway, so then, but this is an interesting combination of the interpreted semantics and the compiled semantics, but we could get something very interesting. Okay, then next thing is threaded code generation. Threaded code is a very old technique, almost 50 years old techniques to generate a kind of a quick compilation mechanism by generating a sequence of handlers. So for example, if we have this kind of source code, then the threaded code generation basically generates the call of the handlers of each corresponding instructions, and which was done by manually making some translators. But I'm going to show this is also possible, automatically enabled by just tweaking a meta interpreter. And so for example, if we have this kind of interpreter definition, then the RPython framework usually generates the compile code in like that. So this is what I have shown as a compilation. But we just add some annotation, don't look inside, which is RPython's special directive, not to trace this side, but leave just a call to this handler. And then we will get this trace, which is actually looks like, and which is actually a trace threaded code. So this is also very interesting. So just one interpreter definition, we can do a full compilation or threaded code generation. And there are also many some dark side to realize this, but let's move on. So the next thing is inline caching. And inline caching is also an old technique to optimize the indirect call by replacing with direct call when it is calling to the same target, which is usually done for the object-oriented programming for method dispatching. So if we do the method dispatching on the same class, then we just insert the direct call to the method body by just checking the class of the target. And for example, if we have without inline caching, if we have semantics of the function call, in this case, I'm going to simplify the function call of the not object-oriented, but the first-class function call, then its semantics is basically going to be get a function object from the stack, and then the evaluate evaluates that function by using the interpreter call. But in this case, the function is dynamic value, so we have no way to compile. So by using RPython, we can get this is going to be compiled into a code, just performs the interpreter call. Inside of the interpreter call, it's just going to dispatch to the just-in-time compiled code. So this is basically, you can understand this is going to be compiled into an indirect branch, indirect jump. And but by using one kind of RPython feature just to generate the direct call and also insert some kind of cache technique. So for the first time, we record the last time. So we record for each call site which function was called, and the next time the call happens, if we are going to call the same function, then we generate a direct call. This is also an interpreter definition. So if we just interpret interpreter execution, it does exactly the same the original execution just by checking the recording and checking. But if RPython actually traces and compiles, then we get this code. So for this part, so when tracing compile happens, then it comes into here, which is compiled into Graal instruction, and then it generates the call instruction. And then if we look this code, then it's exactly the same as the inline caching code. So the first checks the call target was what we actually recorded before, and then directly call the target. Okay, the last thing, which is multi-tier JIT compilation, and which is found in many modern just-in-time compiler virtual machines, which is using the multiple just-in-time compilers. A lower tier is fast, but it produces low-quality code. And the higher tier compilers takes more time to compile, but it generates the optimized code in order to balance between the startup performance and peak performance. And with RPython framework, since RPython actually generates the compiled code based on the interpreter definition, so it can be easily done in principle by providing the different interpreters RPython frameworks. We will get the different compiled code. So multi-tier JIT compilation seems to be easy, but really interesting or really challenging part is how to switch those interpreters within the RPython framework. And in order to do that, we found that when we actually implement a user-level profiling, then we can do the switching the interpreters, which means for example, this is a semantics of the conditional jump instruction, And this is a original definition of the conditional jump, which does nothing, just conditional jump. And and assume this code is written as a lower tier interpreter. Then we insert tracing profiling code like this way. So just count up the execution times for each program counter, and the counter reaches to the threshold. Then let the higher tiers interpreter evaluate the rest of the program. And then the RPython framework automatically compiles with respect to the compiles the higher tier interpreter, which takes more time, but it produces the faster code. Then we realize the multi-tier compilation. And I'm not going to read this dark side, but there are many techniques to realize that. But putting those things together, we actually enable to implement it two-level SOM, simple object machine, which is a subset of Smalltalk, and like in this figure. So this blue box is original SOM implementation, which was around 16 kilolines of code, and we added the first tier evaluation, which implemented the threaded code generation and also method traversal mechanism. And then we also made a driver evaluator, which basically delegates everything to the first tier interpreter, and then we will get the threaded code here, in which we have a user level profiling mechanism and also inline caching mechanism in order to recover some performance loss of the threaded code. Then this user level profiler actually triggers the tracing next level of interpreter, which is original tracing compiler, which we get the faster code. So this is, in the end, this is something similar to the multi-tier virtual machines in these days. And the result is very satisfactory or surprising to us. So we implemented two SOM and compared to performance the original Python with respect to a large application. Then measured the startup performance. Then we found that our implementation actually improves by 15%, which is very nice. And we also lose some performance due to the multi-tier execution, and we found we got roughly 5% peak performance overhead. Okay, so what I've shown was so meta-tracing JIT compilation framework is not just a JIT generator for different languages. That means it can generate the JIT compilers, but we now see by adding something, I don't find any good word but for here, but add something, then we can provide many different behaviors of virtual machine. So beyond the compilers do. So I could say we knew that the partial evaluation of language semantics do compilation, but we also knew that the partial evaluation of virtual machine behaviors, we get something beyond compilation. And I also don't know good word for here, but something interesting. And I only have 10 minutes. Okay, so next part is going to be very quick. Maybe just it's ongoing work, but another interesting use of tracing JIT compiler is an easy backend of multi-stage programming. And I'm going to skip. So what multi-stage programming is, I don't need to talk about this one, but multi-stage programming is just a manual partial evaluation by specifying this part is dynamic code, this part is static code, and those code in those boxes. And the notable implementations are the meta-OCaml and the Scala LMS. But if we wrote an interpreter in meta-OCaml and generate a compiled code with of a factorial program of that simple interpreter program, and executed that program for factorial function for 50,000 times, then we found that this performance. So this is interpreted execution. This is meta-OCaml dynamically compiled execution. Then the compiled code is very fast, 20 times faster than original one, but it takes the 80 milliseconds of compilation dynamic code generation, which is sad because the meta-OCaml actually uses a ahead of time compiler behind the scene. And that means even if the first stage it generates the AST-like code, it converts into string, and then the full compilation happens here, like parsing, type checking, code generation, and so on. So obvious optimization is to generate the AST or even generate the intermediate code during the first stage computation, but which is very heavy. Which is as heavy as hard as we are making another just-in-time compiler. So what we found is just use the lambda closures without modifying the underlying language mechanism. So given this multi-stage program, we propose to convert this program into this program just generates the lambda expressions. So for example, for this part of the code, it just generates a lambda closure that computes the x times the generated code. And then if we provide partially evaluate this function, then we will get this chain of closures, which isn't usually fast because the number of the indirect calls. But by using tracing JIT compiler, this chain of closures is optimized away. And then what we found is that another experiment. Unfortunately there is no tracing JIT compilers for OCaml, so we use PyPy for the comparison. And then PyPy is not as fast as OCaml if we executed by interpreters, but with the lambda staging, by using lambda closures, then we will get this performance, which is actually faster than the meta-OCaml. So which is kind of nice. So from here, from there, I found that we often want to generate code even at runtime. So because that's why many languages have macros, template metaprogramming, or evals, or multi-stage programming. And it seems that the lambda closures and the tracing JIT may achieve both good code generation speed and and the generated code speed. So it might be a very nice place to play with for code generator backend. So then this is the last slide. So I'm going to summarize my messy talk. And so I first showed that the meta-JIT compiler framework can implement VM behaviors beyond compilers. So and there should be many interesting future work like implementing more virtual machine behaviors like special optimization techniques and the language-specific, application-specific optimization techniques. And also, I'm very interested in making a kind of a toolkit for defining those kind of interpreters. And second part is about the tracing compilers can be a good backend for dynamic code generation. And maybe it might be interesting to generate a series of multi-stage languages based on the meta-tracing JIT compiler framework. And what I haven't, so I'm only talked about the RPython, but the Graal Truffle is another meta-JIT compilation framework, and we can also think about the same kind of things based on the Graal Truffle. So that's it of my talk, and thank you for listening, and I'm very happy to get questions.
Very complex things, very unmessy. So thanks for it. I'm Manas Thakur from IIT Bombay. The question I have is, you talked about a subset of small talk. So are there features of small talk or language features in general for which generating multi-tier JITs like this is difficult?
So your question is basically about the difference between SOM and small talk.
Or in general.
Or in general. I don't have a good answer right now. Stefan is here. maybe he can answer after the session, but yeah.
We'll talk later.
May I ask a question about threaded code? You introduced several techniques that can be achieved by meta-JIT compilation. For this threaded code, is this actually benefit for developing virtual machine? Is there any benefit compared to compiling it into the native code?
Oh, I see. I was very bad to talk about, but the threaded code is basically good for faster compilation. And so compared to the, maybe this one. So for the backend of RPython, compiling this trace takes much longer than the compiling this trace. So by using threaded code generation, we shorten the compilation time, which actually benefit for the startup performance. That was the...
Yeah, thank you. So this contribute to the multi-stage compilation?
Yes.
Thank you. Other questions? Or some comments from Stefan?
I was asked about the difference between SOM and full set of small talk.
Questions?
Thank you for the talk. I study multi-stage computing, so the latter part was really interesting. So speaking about the latter part so applying meta-tracing JIT for multi-stage computing, so you said code generation is translated in function in Python. So does it mean that this staging is basically assumed for runtime? So how can I say? So it's basically online code generation where generated code is evaluated at the same stage.
I guess the question is about the.
My question could be: so the code generated power function will be evaluated at the same time, or is so the generated code can be output.
I see.
So and then evaluated in another
the
stage.
question is about whether this is assuming the offline code generation or online code generation.
Yes, exactly.
And I'm assuming online code generation. So for example, this time the 5 is static input, but sometimes the file is provided from the user or at runtime, and then generates the power of 5, then it executes that function at the same time.
I see. Yes, thank you very much.
Okay. Okay, so let's thank to the speaker again.